Hi friend, this is Shomik Bishwas and you are attending my classes of the circuit theory, and today I am giving the lecture upon the concept of tree. Already in my previous lecture I have shown you how the graph can be converted in a tree, how the tree can be converted in a graph, and obviously one tree must be one open path. No closed paths are there in a tree, and the branches of the tree is called the twig, and the closed path, it means what are the particular line or lines can be used to make a number of closed path or one single number of closed path in a particular loop, in a particular graph, is called the tree. Now what is a graph? I have shown you the basic concept of graph, and here number one, I have shown that one graph is there which is having all total 6 number of branches and 1, 2, 3, 4. So 4 nodes are there. 4 nodes are there and all total 6 number of branches. I have marked it 1, 2, 3, 4, 5, 6. Okay. So what is the tree? It is already clear to you. Now see this from this graph. How many trees can be taken care of, can be made? So here for that question number 1, I have shown that if I make the structure like this way, it is a tree. Or if I am taking this 3 point, it is a second one. Or if I am taking not this, suppose if I am taking say this one, it is one. Or if I am taking this one, it is another. If I am taking this one, it is another. If I am taking this one, it is another. Instead of if I am taking this one, so it may be one. Now if I am taking instead of that this one, it is one. Now instead of this, if I am taking this one, so it is one. So in this way different number of tree can be created by a particular graph. Here I have already collected 8 probable numbers that you can see, but the question arises that really only 8 trees are there? Is there something more? Or actually how many trees are existing from a particular type of graph? Is this fixed or it is variable? So obviously it is variable because the number of branches, the number of nodes will giving origination of that number of trees. So here in this particular graph we are having all total 8 number of trees, and maybe a question arises that it may be much more than this. So actually how to determine that how many number of total trees are there? That is completely done by the calculation of that incidence matrix. So here it is a determinant of A transpose. If you are having that A means that AI means that incidence matrix. So incidence matrix, if you are having the transpose of it, so all total whatever the value will be coming is called that NT, the total number of probable trees. Now here I just did this one for that calculation I have already made. So just see this here for this given graph, this incidence matrix I have calculated, and you can also calculate. I have shown you how to calculate this. Then I just find out A transpose. So obviously if it is A, so this is obviously A transpose. Okay. So finally this A transpose and this particular A, when multiplied and the determinant has been taken, so finally the value is coming as 10. How to get that? You can see this result I have calculated as 10. So all total 10 graphs are there. I have taken only 8 in account, but more 2 is there. So now the concept has started for the loop matrix. So actually how many loop matrix, or what is a loop matrix then? So actually in a graph how many loop exist? So different number of loop can exist inside. So obviously you can see here that the total number of closed loop, how many closed loops are there all total in a particular graph. So how to find out the closed loop? We can see that in a particular case, if you are finding out the closed loop, so obviously there are one closed loop, second closed loop, third closed loop, fourth closed loop, fifth closed loop. In this way different number of closed loops are there. So that total number of closed loop when finally gives the rise of that AI. So finally that figure H, I can easily take that the final closed loop means it is a compact of all the probable closed loop in that matrix relation. So obviously this is a loop matrix. But what is a fundamental tie set? What is tie set? Tie set means when you are setting this tie, actually you are here, you are making this way, that one giving example right here, that is we are finding out the tie set. So what is tie set? That in this particular one, if I am removing these three links from that particular graph, so obviously the graph is look like this. So the graph is basically look like this. So it can be one node, it can be the second node, it can be the third node. So these 3 points are the, it means this line and this line, these 3 is the links, and this is the twigs basically. So one tree structure and its probable links, that the combination is called the graph. So when the tie set is there, so you have to get the tree first, and the dotted line will represent its link. Then we are having how many closed loop? Number 1 closed loop, number 2 closed loop. So for number 1 closed loop the current is I1, and for number 2 closed loop the current is I2. Okay. Now accordingly to this we have to set the tie set matrix. So how it can be done? Again, before going to the tie set, one incidence matrix can again rewritten in the form of link and twig matrix, twig and link matrix. So here if you are considering one tree, so 1 5, this is 1 5 and 6, 1 5 and 6, these 3 for this particular one. Here say it is 1 5 and 6, these 3 path if given, so it is basically the link one. So if you are considering one tree, so the tree branches is called the twig. So obviously it is 2 3 4 direction. So here it can be again written as that summation of AT dot AL. AT means this one, the twig matrix, and AL means that link matrix. But here one important thing, that determinant of AT is always plus minus 1. So it is a non-singular matrix. Okay, keep it in mind. But AL is a singular matrix. Now, so what is the condition of that fundamental tie set or F tie set? That for one loop the considered current direction, if same of any branch current orientation, it will be taken accordingly plus 1 or minus 1. Say in this particular one I am just making it enlarged so you can see it well. So if I am considering this I1, so you can see this for I1 here how many points is necessary, that 1 4 and 5. Okay, so here that particular current flow direction if you are considering, so this is plus 1, this is plus 1, this is plus 1. Why this is so? Because if you are taking this first loop, so the current flow is I1, So current is passing through that 1, 4 and 5. So here the current is flowing in this direction and the total net current flow is in the same direction. So obviously all coefficients are plus. If you are considering the second part, and if you are considering the second part, you can see that there is the another part is 1, 1, 0 with the same consideration. Okay, so I am just making it quite smaller. And finally the row entries must be equals to 0. So therefore V1, V4, V5, these 1, 2, 3, these are representing the branch voltages, and I1, I2 is a current of each loop. So if you want to calculate that particular branch voltage and branch current, so from that node point, you can easily jot this one, V1, V2, V3, V4 and V5. These particular values are the V basically. And what is V? V basically the branch voltage. Okay, and this is a loop current I1 and I2. So this entry and this entry must be equals to 0. So V1, V4, V5 equals to 0, first one, and the second one V1, V2, V3, V5 equals to 0, the second one. And finally, what are the branch currents? So this is the first branch current, so I1 plus I2 equals to the I1. For the second branch it is only I2, third branch is I2, fourth branch is I1, and fifth branch this is I1 plus I2 again. So in this way you have to get that final one, and this is, you can see, let me erase this mark first of all, and finally you will be getting all total this one, that what are the branch current and how the branch current is reflecting its balance. So this particular matrix often said as a current or loop matrix. Somebody says in the current matrix, somebody says in the loop matrix. So direction of I1 and I2 must be same. Here whatever the direction I have made in this particular one, you can see if you are observing this one, so I make it quite enlarged, and you can see the direction of I1 and I2 for this one is always same. Here that I1 and the I2 all are taken in this direction. Okay, so I1 and I2 must have that same direction, then only that matrix can be evaluated. So in this particular lecture I have told you what is the basic concept of that tie set and the fundamental tie set, and basically the tie set matrix, this particular conception is used when you are using some KVL evaluation using that graph theory. In future if it is possible, so obviously I will do much more videos on that graph theory, but it is the basic sense. So just you should know that using KVL we are using this type of tie set matrix to evaluate the final value of the KVL one. So that's all for the today's lecture. In the next class I will discuss what is the cut set matrix and how the cut set matrix is calculated by a particular graph. Thank you very much. See you all in my next class.